Hello everyone, welcome to the Fluids Lab introduction. This is the first lab for your EMCH 362 Mechanical Engineering Lab 2. I am Soumya Raghu and I am going to be your TA for this specific lab. My email address is given below and my office hours are also given below. So I'm going to hold these office hours through Blackboard Collaborate Ultra. And these office hours are before the submission of the report and after the graded report has been returned to you. So if you have any questions, please feel free to reach out to me via email or drop by during the office hours. The main objective of the Fluids Lab is to understand the relationship between flow rate and the pressure difference. For us to understand this phenomena, an experiment is designed involving a closed flow loop system. In this system, you can see a reservoir which is filled with water, and you can see a centrifugal pump which pumps the water from the reservoir through the inlet line, which is the bottom line that you see in the picture. It pumps the fluid to the line, which is the outlet line, and through the paddle wheel flow meter, followed by the mechanical valve, and finally to the venturi. So the reason I say it's a semi-open loop, closed loop system is that the water is pumped in through the centrifugal pump, passes through the paddle wheel flow meter and the mechanical valve, and finally get discharged by the venturi directly into the tank itself. So to understand the pressure difference and the flow rate, we have differential pressure transducers that are located across the centrifugal pump, the mechanical valve, and the inlet and the throat of the venturi. So this system overview gives a better understanding of the entire flow phenomenon in the fluids lab. So as we know that the reservoir contains water, the centrifugal pump is going to pump the water from the reservoir and take it to through the paddle wheel flow meter, followed by the mechanical valve, finally the venturi, and the venturi discharges the water back to the reservoir. So the measurements that we are going to do in this lab will contain the first measurement that we are going to do is the power that is required by the centrifugal pump to achieve a certain flow rate. This is by using a Watts Pro power meter. We get the value of the power itself. We also study the flow rate directly from the paddle wheel flow meter. And we also study the flow rate through the venturi tube, which is a venturi flow meter. And as I specified, the main objective of this lab is to understand the relationship between flow rate and pressure differential. We also have the pressure differentials across the inlet and the throat of the venturi. We have a pressure differential across the mechanical valve, and we have a pressure differential across the inlet and the outlet of the centrifugal pump. All of these data are collected by using a data acquisition system of the National Instruments, and we also understand that the mechanical valve is used to control the flow rate of the fluid in the system itself. So to recap, we have the first measurement, which is going to be the power meter, the power measurement of the centrifugal pump. We have three different pressure differential measurements. The first one is going to be across the centrifugal pump, the second across the mechanical valve, and the third across the venturi tube. We will have three different flow rates that we are going to measure. The first flow rate that we are going to measure is going to be through the paddle wheel flow meter. The second flow rate that we are going to measure is from the venturi tube, which is also called the venturi flow meter. And the third flow rate that we are going to measure is going to be the actual flow rate. How do we measure the actual flow rate? To measure the actual flow rate, we use a graduated cylinder and we use the stopwatch. So we use this to calculate three different flow rates. We have three differential pressure measurements as well as a power measurement. So this helps us to understand what exactly happens in a closed circuit system and how the difference in pressure is directly related to the flow rate in the system. So now that we have seen the fluids lab setup, I would like to elaborate on the main objectives of the experiment itself. As I specified before, the main objective is to understand the flow rate and the pressure differential relationship. So to understand this, we have different instruments. We have the centrifugal pump, we have the paddle wheel flow meter, we have the mechanical valve, and the venturi meter. So all of these are connected through, of course, by the pipes. And we have a reservoir through which we supply the water. So our first major objective is going to be determining what the efficiency of the water pump is. So in this case, depending on the flow rate, we would understand how the efficiency of the pump would vary. We'd also understand what the working principles of the venturi are. So we would talk about a little bit about Bernoulli's theorem and how we would come up with the equation to find out the efficiency of the venturi, which is also called the coefficient of discharge of the venturi. So this equation would help us understand the flow rate and the pressure drop in the system itself. Another main objective of this lab is to understand how the values of efficiency will vary for the different venturies. As you know, the venturi contains an inlet, a convergent portion, a throat, which has the minimum diameter, and a divergent portion. So by changing the inlet, the ratio of the inlet to the throat diameter, how does the efficiency vary? This is a major takeaway from this experiment. So whenever we start an experiment, we start with a hypothesis. Hypothesis is essentially an educated guess or a prediction, if you will, before we go ahead and perform the experiment to understand what results we will obtain from the experiment itself. So in this case, we have different variables. We have independent variables, dependent variables, and control variables. The independent variables are essentially the variables that are going to be, controlling the whole experiment. And the dependent variable will depend on how the independent variable varies. So to give you a specific example, whenever we draw graphs, we draw the independent variable on the x-axis and the dependent variable on the y-axis. So we say like f of x, right? So similarly, to give a clearer example, I would say that when we have a flow rate, which is going to be on the x-axis, when the flow rate is going to increase, what will happen to the power that is consumed by the centrifugal pump? It is also going to increase, right? So your power consumption is going to be on the y-axis and your flow rate is going to be on the x-axis. So in this case, the independent variable is your flow rate and your dependent variable is going to be your power. So if you can see, you will see a trend, something like, increase in flow rate will lead to increase in power consumption. So that is how we are going to specify what the hypothesis are for this specific experiment. So the two major calculations that you would be doing in this experiment is computing the pump efficiency and computing the coefficient of discharge, CD, of the venturi. So to find the pump efficiency, we have the formula here. It is delta P Q multiplied by Q over W. Delta P represents the pressure differential that is being measured. So we know that from the previous diagram that the pressure differential sensors are located across the inlet and the outlet of the centrifugal pump. That will give us the measured pressure differential. So we want to make sure that the value that we use to find the efficiency of the centrifugal pump should be measured from the pressure differential that is calculated across the centrifugal pump. We've also measured the flow rate, so we'd use those values, and we will also measure the power across the centrifugal pump by using the watts per power meter. So in this way, we calculate for every trial with a specific venturi with changes in the flow rate, we will calculate what the efficiency of the pump is going to be. Now moving on to the coefficient of discharge, discharge coefficient of venturi, we would see that by using the Bernoulli's equation and by using continuity equation, we have this formula for finding the ideal flow rate of the flow in the fluid system. So we know that Q is equal to the volumetric flow rate is equal to A2U2, and now it is expressed in terms of the area factor as well as in terms of the pressure differential. So here A2 represents the area of the throat and A1 represents the area of the inlet. So in this case, the inlet to the inlet diameter is given as 17.66 millimeters and the throat diameter is given as 8.8 millimeters. So which means that our baseline criteria is for a D over D of 0.5. Now, you would also be given a D over D with a different value ranging from 0.575 to 0.7. So in this case, you will have your capital D, which is the inlet diameter, will remain constant, whereas the small d will vary depending upon what your ratio is going to be. So that is how you will calculate your A2 and A2 over A1 right here. The value of GC is given to you. The value of the density of water, which is essentially 1000, is also given to you. Now to compute the discharge coefficient of the venturi, CD, we actually use the actual flow rate that we have measured and you divide it by the ideal flow rate. So I'd like you to pause for a minute to think about what the maximum value of CD can be. So the maximum value of CD can be always equal to 1, right? Because the actual can be equal to the ideal, right? It can never be greater than 1, right? So your actual flow rate that we measure consists of the different kinds of losses across the pipes, across the operators accuracy and so on and so forth. So your actual flow rate can never exceed the ideal flow rate that is measured by the system. So that is what you would have to take away from the discharge coefficient by learning about discharge coefficient of the venturi. Now, since we have two different venturies and we span it over a range of flow rates, we can study which of the venturies has a better coefficient of discharge. Coefficient of discharge is essentially the efficiency of the venturi. So at a particular flow rate, which venturi behaves more efficiently is what our inference will be from this experiment. So now let us go over the experimental procedure of this fluids experiment. In this experiment, as we know, our semi-open closed loop system consists of the centrifugal pump, the paddle wheel flow meter, the mechanical valve, and the venturi. For us to pump the water from the reservoir, we are going to be using a centrifugal pump. So in this case, we first turn on the pump, we let for it to stabilize, and then we actually take the actual flow rate. So once we take the actual flow rate, we calibrate the other values which are corresponding to the venturi flow rate and the paddle wheel flow rate from the actual flow rate. So once this is done, we actually set up the software and start taking the values for these values that are given on here. So we first take the actual flow rate, And then we go ahead and take the paddle wheel flow rate and the venturi flow rate. All of these flow rates are given in gallons per minute. And then we move on to finding the pump differential pressure across the centrifugal pump, the valve differential pressure across the mechanical valve, and the venturi differential pressure across the inlet and the throat of the venturi. And we also measure the power that is consumed by the centrifugal pump. So we repeat, once we take all these values, we repeat the entire experiment by turning off the pump and changing the valve position and then calibrating it again and running the experiment. That is how the entire experiment is done. I have here given you a sample set of data that have been got in the previous semesters. So you see that we measure the power of the centrifugal pump. So the power is given in watts. The actual flow rate that we measured in gallons per minute. The paddle wheel flow rate is given in gallons per minute. And then the venturi flow rate is also given in gallons per minute. Now we know that the pressure differential, the differential pressures, we have three different values. So that is the pump, that's the valve, and the venturi. So if you remember from the formula that is used to calculate the centrifugal pump efficiency, we would have to make sure we use the pump differential pressure and the actual flow rate with the power. And if you remember, for the calculating the CD of the venturi, we would have to use the venturi differential pressure, and the ratio will be the actual flow rate to the ideal flow rate, which is actually measured by the venturi itself. Our major inferences from the entire experiment is based on these three research questions. There are some other sub questions which are answered along the way. But the major questions that you would have to answer is how is the flow rate related to the pressure differential across the venturi tube? And similarly, how is the flow rate related with the pressure differential across the paddle wheel flow meter as well? Now that we know about the pressure differential and the flow rate, we then move on to the efficiency. So in this case, we will talk about the two different venturies with two different D over D ratios, one of which is 0.5 and one of which is going to be assigned by your instructor. So you will talk about as the flow rates increases or decreases, do you see a trend or do you see which venturi performs better? And similarly, and with the change in the venturi D by D, how is the pump efficiency changing for a certain flow rate range? Um, so these are the primary research questions that you will be answering along the way while you write the report. And this is what I'm looking for in the conclusions as well as your results in the abstract. So now let's move on to the tabulation that is required for your lab. The tabulation is for the different D over D ratios. You can see that there are two D over D ratios that you would be using. The actual flow rate, so all of your data is given in gallons per minute and PSI. So you would want to convert it into SI units. So you keep it in meter cube per second for the flow rates. So the three flow rates, which are actual, venturi, and the paddle wheel flow rate, will be converted from gallons per minute to meter cube per second, followed by you will convert the pressures, which are given in PSI, to Newton per meter squared. So you'll convert all of these pressures to Newton per meter squared as well. Now we would calculate the CD. We know the definition of CD, which is going to be the flow rate, which is going to be the actual flow rate over the ideal flow rate. So in this case, the actual flow rate is the actual flow rate that is measured. The ideal flow rate is the venturi flow rate. So you will calculate the CD of the venturi for the various flow rates. And finally, you will calculate the pump efficiency, which is given in the formula delta P into Q over W, which is the product of the pressure differential into the flow rate over the power that is consumed by the pump. So these are the calculated values, as you can see, which is highlighted in a different color. And these are the values which you will do the conversions for. Now, in the upcoming 3 slides, we will be talking about the graphs that are essential for a complete understanding of this lab report. The first graph is going to be the trial number versus the flow rate. For every venturi, we are going to be conducting 5 different trials with the whole experiment itself. So we will plot the actual flow rate, the paddle wheel flow rate, and the venturi flow rate as a trial number, as a function of the trial numbers. So we will do this for both the venturies. So in means of graphing, so if you're doing the graph in a um, single graph, you will have 6 different lines. Or if you choose to do it in 2 different graphs, you will have 3 lines in each of the graphs. So you can choose to do in either of the methods, but specify what D over D ratio that you're correspondingly plotting in the figure title. Moving on, the next is going to be comparing the actual flow rate versus the pressure difference. So in this case, you will observe that if you remember from the equation of the volumetric flow rate, you see that the volumetric flow rate is directly proportional to the pressure difference in case of the Venturi flow meter. So in this case, you will see as there is an increase in the actual flow rate, there is going to be an increase in the differential pressure in dP between the inlet and the throat. Whereas if you observe the pump and the valve, you see an inverse proportionality between the actual flow rate and the um, pressure difference. So as there is an increase in the flow rate, there is going to be a decrease in the um, pressure difference. So if you think about it physically, itself, you will the physical phenomena itself, you will see that as you open the valve to the maximum position, you will see that there is um, lesser resistance, causing it to have lesser differential, causing it to have a lower dP. So similarly, this is how you would go about explaining what your inferences are from your lab itself. Now we move on to the specific results related with the Venturi tube. We will plot a graph between the actual flow rate and the Venturi flow rate. Um, and this will be for both the 2 difference d over d that has been assigned to you, the baseline and the assigned d over d. Um, Now you will see, it should be able to see a linear trend as the actual flow rate increases. You should be seeing a linear trend about 45 degrees if your actual flow rate is correspondingly almost equal to the Venturi flow rate, which means your losses are very minimal. And this will also be reflected in plotting your CD versus flow rate. CD is essentially the efficiency, which is actually given by Q ideal, which is Q ideal is going to be your Venturi flow rate, and Q actual is going to be the actual flow rate you measured. So your Q actual over Q ideal will give you the CD, which is the coefficient of discharge. These two are the essential graphs for the Venturi tube. Next, we move on to the results required for the centrifugal pump. In this case, since we've already done the graph with the difference in pressure versus the flow rate, we move on to the pump efficiency versus actual flow rate. In this case, you would also have to plot for 2 different P over D ratios. So you will have 2 different curves on the same graph, comparing the pump efficiency for the 2 different venturies as the flow rate increases. So you should be able to see this trend of increase in pump efficiency as there is an increase in the actual flow rate. Our final discussion points are going to be with the paddle wheel flow meter. We are going to compare the paddle wheel flow rate versus the actual flow rate to see that if it is following the same trend as that of the Venturi itself. So there is a proportionality that is involved in measuring the actual flow rate and the paddle wheel flow rate. And there are some losses that are incurred while the measurement is made as well. So I would like to conclude with a few report writing tips since this is going to be the first report of the semester. Please keep the entire report very concise and clear and to the point. I have specified the tabulation that is needed, the graphs that are needed, and the results that is being inferred from the whole lab report. So please do maintain the lab report format that's been given to you, and then make sure that you write concise paragraphs, uh, probably 4 to 5 sentences per paragraph. Another important tip is please use equation editor. Please do not copy paste or just snip and paste from the lecture notes as a picture. And since there are different points that carry for your formatting itself. And then the tables, please have your table number and the table title on top of the table. And the figures and graphs both are named as figures, and their figure name and the figure title should be below the graphs itself. So these are some of the tips that will be very helpful while you're writing the report. To summarize, we understand the basic functioning of a fluid flow system, and we extrapolate it in understanding the relationship between the pressure difference and the flow rate through a semi-open closed loop system. And our major takeaway is how does the change in the diameter ratio, D over D ratio of the venturi tubes influence the efficiency of the pump, as well as which of the chosen venturies gives us a better efficiency or CD at a specific flow rate. Also, from this simple experiment, we can understand what the drawbacks of the systems are, because there are losses at the pipes, there is friction losses, there is losses due to the connectors in the pipes, and so on. And also, we can propose what other enhancements can be done to this system to understand the flow itself. So now we also have to understand that whatever we are doing in this lab is essentially a steady state flow, and it is incompressible as well. All of these concepts that we have studied applies for steady state incompressible flow phenomenon. Thank you, and please feel free to reach out to me. I've given my email address here, and I've also specified my office hours. Good luck with the lab, and thank you.